Hi, this is Group 1's video for the PHAS 0035 task. Our topic of discussion are the Carnot and Otto cycles from our thermodynamics module in Year 1. If we consider an ideal gas between a hot and cold reservoir, it goes through four processes in a Carnot cycle. Initially, the gas is in contact with the hot reservoir and heat is added to it. Then the gas is disengaged with the hot reservoir and then comes into contact with the cold reservoir, where it rejects the heat. It then loses contact with both reservoirs, and since there is no net heat transfer, it reverts back to its original state. Here is a simplified model of the cycle. Since the gas reverts back to its original state, there is no change in internal energy. The efficiency of the system can thus be calculated as 1 minus the ratio of heat transferred to the cold reservoir over that transferred from the hot reservoir.
Now we can talk about two different cases. The first one is going to be when we have two identical Carnot engines. This means that one engine is driving the other. So we have heat coming from the hot reservoir and then producing work, which is going to drive the heat coming from the cold reservoir and turn it into heat that goes into the hot reservoir. This basically implies that the modulus of QH is equal to the modulus of Q prime H, and the value of QC is equal to the value of Q prime C. Now let's imagine another scenario, which is going to be the case too, where one Carnot engine is more efficient than the other. In that case, we have the efficiency N is bigger than the efficiency N prime, and since we have N equal to the work divided by QH, we basically get QH is smaller than QH prime, and QH prime minus QH is bigger than 0. This violates Clauss's statement, which says that it's impossible to transfer heat spontaneously from cold reservoir to hot reservoir without any other changes, which means that there is no engine that is more effective than the Carnot engine. Now we can talk about the Carnot efficiency for an ideal gas, and we will refer to the PV diagram. According to the calculations, we get that N, the efficiency, is equal to 1 minus Tc over Th.
To define temperature from the Carnot engine, we can consider a string of connected Carnot engines like the one shown here. Efficiency is given by the first equation. From the efficiency, we have the relationship T1 over T2 is equal to Q1 over Q2, and T2 and T3 are given in terms of T1. This gives a definition of temperature that is independent of working substance. The Otto cycle approximates the thermodynamics of a petrol engine. The figure below shows how the thermodynamic cycle of the Otto engine operates. Air and fuel are injected into the cylinder at a constant pressure. Using external work, the mixture is compressed in an adiabatic process, shown by the path from A to B. When the cylinder is at maximum compression, the fuel-air mixture is ignited to add heat in an isovolumetric process, shown by the path from B to C. Then work is produced by adiabatic expansion, shown by the path from C to D. Lastly, in an isovolumetric process, heat is rejected to the walls of the cylinder, shown by the path from D to A. The efficiency of the Otto cycle is given by the first equation, and can be rearranged to form the second equation. To achieve maximum efficiency, V2 must be much smaller than V1. In practice, the fuel-air mixture heats up and compresses adiabatically. This may lead to self-ignition, so heat is added. This means that the maximum efficiency is limited to around 30%.
Hello everyone, welcome to my section. My part is about entropy. Let's start. Here are the formula of the reversible Carnot machine and the unit of the entropy. Q over T is the ratio of the heat absorbed and realized during a isothermal process to the temperature of the reservoir. So the conclusion is in a reversible Carnot circle, the heat and temperature ratio sum to 0. Any reversible circle can be seen to consist of many reversible Carnot circles. Look like this PV diagram. We draw a circle, and now we have a dirt Qi and dirt Qi plus 1. Use the equation, we can get the conclusion about for any reversible circle, the sum of the heat temperature ratio is 0. Entropy is a function of state. Using the diagram and formula, we can we can get the equation of SB minus SA equal to dQ by T integral. Here is the definition of the entropy psi S, and the physical meaning of it. dQ by T is of any reversible process between initial state A and final state B. Enthalpy is an oscillator system never decrease, so the delta S is always bigger than 0. There are two different situations. One is delta S bigger than 0. Another one is delta S equals 0. When delta S equals 0, the enthalpy is constant. Another situation, enthalpy is increased. The relationship also between the enthalpy principle and the second law of thermodynamics.